Yeah, comes on your own. Let's start off. Great. Let's go ahead with the problem. The last thing that we did, we started with things rotating and moving, and I hope you remember the process. Process is important. Step one: choose a system, draw an FBD, assign linear and angular accelerations, use constraints and no slipping conditions. Apply F is equal to ma, apply torque is equal to I alpha, and solve the equations. This was the theme, right? So, and we have done few questions on that. Let's see a few more. So let's say we have a cylinder here. We have a block M. So we have a string here which is wrapped around the cylinder. Mass M, radius R. Solid cylinder. Gravity is there, and there's no slipping. Now this thing, right, we will discuss a bit. No slipping between string and the cylinder or pulley. So what do you mean by this? So the thing is, till now, right, all the problems we have done so far, able to hear me, right? Yeah. So in all the problems that we have done so far, right, the pulley was always smooth, if you remember in NLM and everything. So what was the difference? The difference was this. See, if you look into my screen, right, suppose this water bottle which I have, if this was like a pulley, you can see there. So till now, what was happening, the pulley was smooth and my hand was the rope. So when I say the pulley is smooth and when the blocks are moving, my hand was simply sliding over the pulley. You're getting it? This is slipping actually. This is how the strings were going till now. They were slipping. But if you actually see in real life, right, when you put a pulley and put a rope, in reality, right, this is how it goes. If this was the rope touching it, the whole system rotates with it. Are you getting it? The rope is sticking to it, and when it rotates, it takes the rope with it. So there's no slipping between the rope and the surface. So if I have to show you, it kind of looks like this. This is important. If you take a smooth pulley or a cylinder, and let's say there's a rope on top of it, right? So if I take this point to be A and this point to be B, this point to be P and this point to be Q. So it's a smooth pulley. So what will happen when this is moving? In this case, the pulley does not rotate. So when the rope is sliding, this is what you will see. So the pulley, smooth pulley, now A will be here, B will be here, but now P will be somewhere here and Q will be somewhere here. You're getting how it is? The rope is moving. So A and B are points on the pulley and P and Q are points on the string. This is what we have been doing so far in all of NLM and everywhere. The pulley was smooth. But what if you have a rough pulley? Now, when you have a rough pulley, there is actually a friction between the pulley and the this thing. So the picture would actually kind of if I just separate them, this is what you will notice. There is a friction between them. So two things will happen. So here, if you take the tension to be T, here also the tension will be T. Same tension. But here you will notice if the tension is T1, there is a friction between them. Again, depends on how you are rotating. And this friction would be like this. And the same thing, by third law, the friction will be this way. So the friction is actually rotating this pulley also now. On this side, the tension will be T2. T1 is not equal to T2. Right? T1, T2, the tensions will be different. So whenever you're drawing an FBD, when the pulley is rough, you have to take different tensions T1, T2. They can be equal, but they'll not be always equal. So be careful with that. In a smooth pulley, on both the sides, you can put tension T and T. But on a rough pulley, both the sides, the tension need not be same. You have to put T1 and T2. So here the picture will look like this. So A will come somewhere here. P also will be here. Right? B will be somewhere here. And Q also will be somewhere here. Matlab A and P, B and Q will always go together. You're getting it? The pulley has rotated. In this scenario, pulley didn't rotate. Are you clear with the difference? So when you have a rough pulley, two things happen. One, the pulley is also rotating, so there's no slipping there. Second, the tensions on both the sides need not be same. When you have a smooth pulley, the pulley never moved actually. The pulley was just there like a fixed thing because there was no friction or anything to rotate it. Is this difference clear, everyone? Right? And how do you know whether the pulley has friction or not? Look for the word no slipping. If they use the word no slipping, it is a rotation ka problem. It is not NLM. If they mention smooth pulley, it is an NLM ka problem. Let's see how to do this thing. Take a minute, give it a try, then I'll show you one model, then I'll ask you a few more on this. Then we will also learn a shortcut like where you can get the answers a little faster for certain models. Yeah.
So what do we have to find in this?
Find the just leave a message, Nare. Big deal. You don't like typing, yeah? Find acceleration of the block. I'm just explaining. I didn't even start the question. Okay. Find acceleration of the block. I thought seriously you're asking something interesting. I was like, okay, fine. What he's going to ask? I was curious. And
Sorry,
you
sorry.
simply said, like, what? No, don't be sorry. I'm just saying. वो होता है ना anticipation, you're going to ask something करके. And suddenly it was like, shh. So let's get this thing. This is the standard model, mains level. Okay, let's see. Let me show you one model. Step one, choose your system. Block is my system. Disk is, the cylinder is my system. If you see, right, every time I keep telling you the same steps, this is how you actually get it ingrained. You're getting it. Who is this? Right? Someone is asking cone. Cylinder, right? Read the question. Let's see. Why will it be a cone? Solid. Yeah, not a cone. So step one, choose your cylinder and the block. Write the forces. We have tension here, T. This also will be tension T. You have your own weight. You also have this tension on the top string, which we don't require actually, but it is there. And mg. Bus, these are the forces. Step two, assign accelerations. Let the block go down with a. Let this thing rotate with alpha. It can't go up and down because it's fixed. That's step two. What is the relation between them? Now find the relation between the accelerations. Now look at the cylinder. If this guy is going to rotate with alpha, this point is going down with r alpha. That's your A tangential. Now that string is connected to the block here, and this point is going with the acceleration of the block. Since it is not slipping, this point here, let's call it A, and this point here, B, must have same acceleration. Since A and B are in contact, or you can say since they're not slipping, that is the meaning of no slipping. The point where the string touches the pulley and the pulley will have same acceleration. Acceleration of A must be equal to acceleration of B, which is R alpha must be equal to the acceleration of the block. Is that making sense? Don't blindly write A is equal to R alpha every time. Why? I'll tell you. What if tomorrow they give a question like this? The pulley is placed in a lift and the whole lift is going up with A naught. And then if I say there is a block M here, now what do you think will be the answer? So when I take the pulley, and if I say this is rotating with alpha, this point will have an acceleration R alpha, but since it's already going up, it will also have a lift ka acceleration A naught, and this is connected to the block. This will be A block. So now the relation will be R alpha minus A naught is equal to A block. Did you see how the answer changes? That would be the no slipping condition. So be careful. Don't write A is equal to R alpha. This is something, becomes like an habit, right? What is no slipping condition? V is equal to R omega. A is equal to R alpha. It's a blunder. What is no slipping condition? At the point of contact, they will have no relative motion. Done. So same velocity, same acceleration. Keep it simple. Then step three, write the force equations. Now for the pulley, there is no point in writing the force equation. So I can write directly the torque equation. I will write torque about the center. So if you take torque about the center, T dash is 0, mg is 0, this will be T into R. That will be equal to I into alpha. For a solid cylinder, I about the center is mr square by 2. T is equal to mr alpha by 2. This is equation 1. Here mg minus T is equal to ma. This is equation 2 and this is equation 3. You're done. Take T here and substitute. This will be mg minus mr alpha, but r alpha is A, ma by 2 is equal to ma. We get A is equal to 2g by 3. Easy. A will act at center of mass, right? I didn't understand what you're asking.
So, like you wrote A naught up in upward direction, but
That is a translation motion, right? Ta-da! You forgot no slipping condition. So when I say the body is going with V and omega means what? Every point is going with V, isn't it? You superpose, na? Translation plus rotation. All clear with this? Easy question. But there's a much faster way to do this. I'll show you that. But first, let's get the process right. Any doubts on this? Again, did I teach you anything new? FBD, equation constraint. This is something new. The no slipping, rough pulley, smooth pulley. This is a new discussion though. Let's see one more. Again, solid cylinder, M and R, no slipping. Find the acceleration of the blocks. 2G by 7, 2G by 7, maybe right, Arya, Samyak, I think. Let's see. Step 1, to draw the FBDs. Let this be T1, this would be T1, this would be T2, this would be T2, 2mg, mg. Let this rotate with alpha. This guy will be acceleration. This also will be acceleration. Accelerations will be same, huh? Because the string is length of the string is constant. If this guy is rotating with alpha, this point is going with R alpha, and this point is going with R alpha. This point is going with A. So it's not slipping. A is equal to R alpha. Write the equations, take torque about the center. Remember, T2 ka torque and alpha ka direction are same. You have to be careful with the directions. T2 ka torque is minus k cap. Alpha ka direction is also minus k cap. So T2 will take it as positive and T1 will take it as negative. That will be mr square by 2. So that will be mr alpha by 2. And A is equal to R alpha. That will be A is equal to MA. This will be T1 minus mg is equal to MA. This will be 2mg minus T2 is equal to 2ma. Right? You want to find A, so you can just add them up. We get T1 minus T2 plus mg is equal to 3ma. But T2 minus T1 is minus ma. Did I miss something? T1 minus T2 mg plus mg 3ma. T2 minus T1, that is ma. Yeah, I did something wrong actually. Wait, did I go for?
Sir, you took MR alpha upon 2 as MA.
Yeah, right. There I goofed up. A is equal to 2 by 7. Clear with this. Just have a look at this. Great. Now, how do we solve these things faster? So listen, if you guys remember in NLM, I taught you something called net force method. Similarly, here we have something called a net torque method. Because if you notice something, when I solved the previous question, right, in order to find alpha or A, we never actually cared about T1 and T2. So this T1, T2, right, really won't matter. Then we can do something. This is the formula. Alpha is net torque by total moment of inertia. Again, whenever you get a shortcut, there is always a certain limit. This is valid only for single pulley. If you have multiple pulleys, right, then we have different things. So how does this work? So let's say we have blocks M1, M2. Let's say this is M and R. So step one, what you do, let me take the example of the previous one only, better. This is M and this is 2M. So tell me one thing. Suppose if I put the block here or if I put the block here, does the length of the string affect the problem? The length of the string is not affecting the problem. So since length of the string is not affecting the problem, take these blocks in such a way the length is almost zero, attach the blocks at the point where the string is connected to the pulley. Means you treat this particle 2m stuck to the pulley, treat this like a particle m stuck to the pulley. Right? So replace the blocks with particles of same mass. Right? And attach them to the pulley where the string meets the pulley. Right? Now, if you try to draw the FBD, look at the forces. This is mg, this is 2mg, this is anyway mg here. So if you take torque about the center, so assume any direction you want. I'll assume alpha in this direction. So ask yourself, is 2mg helping alpha or opposing alpha? 2mg is rotating in the direction of alpha. So torque about the center will be 2mgr, force into the perpendicular distance, minus mg into r, because mg is opposing the thing, right? And this will be I of the whole system. What is moment of inertia of the whole system? Remember, what is the system? The two particles and the pulley, which is I of the pulley, moment of inertia of mass m, and moment of inertia of mass 2m. Pulley ka moment of inertia mr square by 2. This is mr square and this is 2mr square. Therefore, alpha will be torque by I of the system, which is mgr by 7 mr square by 2. 2g by 7r. A is equal to r alpha for no slipping in this case, and you'll get the acceleration from there. Is that clear, everyone? So you can use this when there's a single pulley. You just replace the particles there and finish it off. Understood. Same thing. If I give you one more example, this problem which we did, the first one, this was M and this was M and R. Same story. Take the thing, take this mass, attach it here M. So this will pull with mg, your own weight mg. You take torque about the center. That will be mgr. That will be I of the system, which will be mr square by 2 for the pulley. For the particle is mr square alpha. This is for I pulley. This is for the particle. Particle ka moment of inertia is what I meant to r square, the distance. Alpha is equal to 2g by 3r. Clear with this? So if you remember in NLM, we did something similar. We called net force method. That was valid when all the blocks had same magnitude of acceleration. Remember? You should check it out in case you forgot. So let's see a question based on this now. So this thing saves you time. Find the acceleration of the blocks. Yeah, let's get the acceleration of the blocks. Hmm. Right, Arya. Right, Samir. Get this. If you use the method which I taught, you don't take much time. There is no need to write any equations, nothing. You can finish off it fast. Let's see. So what do? We replace the blocks. So take the pulley. You have to replace them at this point here. So this will be 2 mg. This will be mg. Remember, it is passing through the center. And this is also mg. So when I take torque about the center, only 2 mg is acting. The remaining two are passing through the center. It is 0. What is I of the system? The pulley is mr square by 2. Now remember, even the torque is 0, moment of inertia will add up. Therefore, alpha is equal to torque by I. That would be 4g by 7r. Acceleration of the blocks A is equal to r alpha, 4g by 7. Okay with this. Same thing here when you take the pulley. Now, when you attach the masses here, remember they're at something like this. So this is m2g sine theta 2. This is the center, that is m1g sine theta 1, cos theta 1. Your own weight, capital Mg. And let this rotate with alpha. So I'm taking alpha clockwise. So that is positive. So alpha will be torque m2g sine theta 2. That guy is supporting. The pulley is mr square by 2 plus m1 r square plus m2 r square. Moment of inertia doesn't care about your orientation. It is simply the perpendicular distance from the axis. Check your answer. Yeah, if you have taken alpha in the other way, it is fine. That m1g sine theta, m2g sine theta, whichever is bigger, the sines will take care. Are you clear with this? Yeah. Let's see one more like this. What if you have a pulley like this? This is a step pulley. Picture will look like this. So these pulleys, right, have actually different levels. Yeah. Can you see how it is? So depending on where you're keeping, you have different radius here. So this radius is R1. The outer radius is R2. The moment inertia of the pulley is I only. Find acceleration of the blocks. Now remember, this is still a single pulley. It works. Give it a try. Yeah, no slipping, no slipping. If I don't mention anything, it's no slipping. Obviously, right? Now we are doing that only. R1. Right, Aryan. Yeah, right, Aryan. Try. Other, I'll give another 30 seconds. Let's see. So what do? We just connect the masses on the here. That would be M1G. This would be M2G. This was R1. This was R2. Straightforward, no? So I'll assume alpha clockwise. So alpha will be total torque, which is M2G R2, M1G R1 by total moment of inertia. I of the pulley is I. This is M1 R1 square plus M2 R2 square. There, like I said, without writing anything, you can just see and tell the answer. What is the acceleration of this block? Acceleration of the first block will be R1 alpha. The acceleration of the second block will be R2 alpha. Clear with this? So this will be proper mains level equations. Saves you time, but you won't be so lucky every time like this. So let me ask you something else where this doesn't work. So if I start putting 2 or 3 pulleys, this will go off. But all clear with this method? So understand, shortcuts are good, but understand when they work and when they don't work. If you blindly use it everywhere, you will be trapped. Let's do this. Let's say we have a pulley here. So we have a string here wrapped around this pulley. Then it goes over a small pulley and then it goes over a block. This pulley ka mass is 2m, radius is 2r. Solid cylinder, this is mass m and radius r. This is solid cylinder. There's no slipping anywhere. Find the acceleration of the block. How do we now? Here you can't use a shortcut. Go back to the process. Choose your FBD. So there are 3 FBDs you have to draw: 2 pulleys and 1 block. Assign accelerations. Find the relation between them. Write torque equation for the pulleys and write force equation for the block. Solve. The process which I gave you, it works for everything. Shortcuts and all are they're like kind of like shortcuts, for certain models and everything. That's what I'm saying. Your standard method should be always you should be thorough with it. 2g by 5. Okay. I don't remember the answer actually. Let's see. Anyone else got it? Hmm. 2g by 7. Let's see the FBD. Let's see whether you got it right. That you must have done by now. So the big pulley the small pulley, the block. What are the forces? Tension. So let this be T1. So this will be T1. This will be T2. This will be T2. Hope you have taken different tensions. Because there is no slipping, all have friction, so tensions will be different. And you have mg. I am not writing the weight of the pulleys because anyway they're not moving. Next thing, let this guy go down with acceleration A. Let this go with an acceleration alpha 1. Let this go with an acceleration alpha 2. There is no guarantee they'll have same alpha. Now, if you look at the no slipping condition, remember the string is going something like this. So this point here is going with 2r alpha 2. This point here is going with r alpha 1. This point is going down with r alpha 1, and this point is going down with a block. Since it is not slipping, the acceleration of the string along that must be same. So a is equal to r alpha 1 and r alpha 1 must be equal to 2r alpha 2. This is your no slipping condition. So there, as expected, alpha 1 is not equal to alpha 2. Alpha 1 is equal to 2 alpha 2. Please check these things. This is the first step, FBD constraints. Any doubts still here? Then when you write the torque equation for this guy, I'll call it 2 and I'll just call this 1. So torque about 1 will be T1R minus T2R is equal to I alpha 1. That will be T1 minus T2 into R. I1 will be MR square by 2 alpha 1. So we get T1 minus T2 is equal to MR alpha 1 by 2. This is your equation 1. If you take torque about 2, that's only T2R is equal to I2 alpha 2. I2 will be mass is 2m, remember? So mr square by 2, but m is 2m, r is 2r by 2 alpha. Then this is also T2 2r. You have to be careful with the radius. 1 2r goes off, 2 goes off. You also end up with T2 is equal to 2mr alpha 2. This is equation 2 and this is your equation 3. And this guy will be mg minus T1 is equal to ma. This is equation 4. Yeah, that's a little amount of work. 4 equations, 4 unknowns, T1, T2, 5 equations actually. These are 2 equations here. So 5 equations, 5 unknowns. Please check your equations. If you got all this, your job's done. Now it's just a matter of solving. Any doubts on these steps? Any equation you're not clear? Clear? So yes, let's solve this. T1 minus T2 is equal to MR alpha 1 by 2. T2 is equal to 2MR alpha 2. Mg minus T1 is Ma. A is equal to R alpha 1 is equal to 2R alpha 2. Great. So just let's replace everything here. T1 minus T2. R alpha 1 will be Ma by 2. T2, this will be also Ma. 2R alpha 2 is A. There I eliminated alpha 1 here. Mg minus T1 is equal to Ma. Perfect. You're done. Take T2 here, substitute. Take T1 here, substitute. So T1 will be Mg minus Ma and T2 will be Ma is equal to Ma by 2. A is equal to 2G by 5. Yeah, right, Utsa. Right, Arya. Samik. Got it. Clear with this. Any doubts on this? So main thing are the equations. Are you clear with this? So if you have more than one pulley, you can't use that method which I taught you. because now alphas will start changing. So you can't directly say alpha is equal to net torque by net moment of inertia. Clear with this? Any doubts on this? Clear na, Tanishka? Shreyan? Rudransh? Srihari? Clear? Vanchika? Vedika? Clear? Let's see one more. Now we will slowly start going into rolling. Let's say there is no slipping. This is a solid sphere. Mass M, radius R. This is your center. You are applying a force F here at a height h from the center. First question. Find acceleration center of mass. Find friction. Find the direction of friction for different values of h. Find a mu minimum for no slipping. There, let's get them all. Again, remember the process. Step one, choose your body, draw the FBD, assign accelerations, relation between them, force equation, torque equation, solve. Try. Take 2 minutes, then I'll show you. How did you get 5F by 7M, Ray, without H? So you're saying your answer is independent of H? Pado, you know how to do questions, you just don't read them. Fast khatam karna hai. Don't do that. Good thing you're not a doctor. No, Srihari, that is completely wrong. Why did you take friction on the ground? God, there is a friction on the ground. Let's see your FBD. If you draw your FBD wrong, the whole question is gone. So that's something I keep saying. If your FBD is proper, right now in loss of motion, your FBD was almost 50-60% of the problem. In rotation, your FBD is almost 30% of the problem. So what are the forces? Your force F, your mg, your normal reaction, and friction. Now, friction ka direction I don't know. Take it. Science will take care of it. Next thing, SN accelerations. Acceleration of center of mass, alpha. Then find the relation between them. You know the acceleration profile. So at this point, because of translation going forward, because of rotation, you're going backward. And this point is a ground, which is at rest. I'm sure in school, in your classes, right, if you have done this chapter already, you must have written the things very fast. But this is where people get trapped. You have a habit of writing A is equal to R alpha. They don't know, they think, where they got A is equal to R alpha from. People think A is equal to R alpha came from circular motion. A tangential is equal to R alpha. What people don't realize is A tangential is R alpha, agreed, but here because of no slipping, A center of mass becomes A tangential. And that becomes R alpha. Are you getting it? So be careful with that because you will need this. Next question, you will see what happens. So A center of mass is equal to R alpha. That's your no slipping condition and the constraint. You're done. Write the force equations. F minus F is equal to ma. But whenever you have this kind of a rolling motion, right, there is one beautiful point where it will save you time, the bottommost point. You will get the answer in one step actually, right? So if you take torque about point A, now why about point A? Since it is not slipping on the floor, acceleration of A is equal to acceleration of the ground, right, tangentially. And what is the acceleration of the ground? Which is 0. Therefore, acceleration of A is 0 horizontally. Right? But let me ask you something. Is acceleration of A 0? So this is something we need to discuss because acceleration of A is actually not 0. Maybe initially it is 0, but it is not 0 after some time. Now listen carefully here. Let's say after some time, this guy is going with alpha and this guy is also rotating with omega. So if you actually look at this point A, it has A center of mass forward. It has A tangential is equal to R alpha backward. If you remember acceleration profile, I told you, every point will have 3 accelerations. A centripetal omega square R. So the point A, actually A center of mass and R alpha will cancel. A is actually accelerating with omega square R. But interestingly, this thing passes through the center of mass. So when you actually stand on A, you have to apply a pseudo force. A is accelerating. It's a non-inertial frame. This thing saves you time actually. But center of mass is always the best point to take. It is non-inertial, so we have to apply pseudo force. So if an observer is standing on A, this is the center of mass. Where do you apply the pseudo force? We have to apply the pseudo force on center of mass, which will be mass of the body, acceleration of the observer A, opposite to it. This will be mass into acceleration of A. This is the pseudo force, and this thing passes through point A. I know it looks like a lot of work, but at a mains level, this thing will save you a lot of time. Therefore, torque of pseudo force about center of mass is 0. About point A is 0. You cannot do this for any other point. For every other point, the pseudo force will not pass through that point. So now coming back to the question, so if you see horizontally, there is no acceleration. A is very nice point. So if you take torque about point A, torque due to N is 0, torque due to F is 0, torque due to mg is 0. 3 torques are gone in one step. Remember, this total distance will be r plus h. That will be simply F into r plus h. And be careful, if you're taking torque about A, then you also should take moment of inertia about A. That will be F into r plus h. What is moment of inertia about A? I center of mass, 2 by 5 mr square plus mr square, parallaxes theorem. Therefore, alpha will be F into r plus h. Moment of inertia of a solid sphere, 2 by 5 mr square, 7 by 5 mr square. 5f by 7r square r plus h. Acceleration of center of mass is equal to r alpha. 5f by 7 mr into r plus h. There. Did you see what happened there? I didn't write any force equation, nothing. If you take torque about the bottommost point, you'll get the answer in one equation. But you should know this discussion. Huh? A is not an inertial frame actually. It works out because the pseudo force also goes off. These kind of questions will get statement questions. Can you write torque about point A? Right? They'll ask something like that. So is A an inertial frame? A is not an inertial frame. A is accelerating, but it still works because of this reasoning. Are you clear with this? Yeah, but you don't want to do all this discussion. You can go with the regular steps. You can always write torque about center of mass. That will work. Even if it accelerates, then you can write the force equation. F minus F is equal to ma. Torque about center of mass will be F into h plus friction into r is equal to I alpha. Two equations, three equations, solve. You'll get the same answer. You can check it out and see. Is this clear, everyone? So keep this in mind. If whenever you're rolling on a floor is at rest, you can take the torque about the bottommost point. It saves you time. Sure with this? Any doubts on this step, please ask me. Any confusion on why did I take A? You can take any point. It will work, but you have to include a pseudo force. But A is special. A will have three accelerations. A center of mass and A tangential, they'll cancel because they're touching the ground. A center of mass minus A tangential is equal to A ground, which is 0. So there is a centripetal acceleration though. Clear with this? Then what? Once you got A, you can get everything you want. F minus F is equal to ma. So we get friction is equal to F minus ma, which is F minus ma will be 5F R plus H by R 7R. Take out F common. Then that would be 1 minus 5 by 7R minus 5H by 7R. That will be 2 by 7. So F by 7, 2 minus 5H by R. This is your friction. And they can ask you this question also. At what height the force should act so that the friction is 0? If F is 0, we will get H is equal to 2R by 5. That means depending on where you're applying the force, the friction will change. So if your height H is greater than 2R by 5, right? If H is greater than 2R by 5, so friction will become H is less than 2R by 5. The friction will look like this. Friction will act in the forward direction. F is forward. If force is also forward, friction is also forward. If H is equal to 2R by 5, friction is 0. So this is another kind of question they can ask you. At what point the force must be applied so that it will never slip independent of value of the force? Means even if I apply infinite force, the body should not slip. Where should I apply the force? 2r by 5. For a solid sphere, if you take a hollow sphere, the number will change again. Suppose if h is less than 2r by 5, in this case, friction will be backward, force will be forward. So friction direction is not constant. It depends on where you're applying the force. Is that clear, everyone? And once you got this, F must be less than equal to mu into mg. So this will give you the mu ka value also. If you take F greater than equal to 0, 2 minus 5h by r, h will be less than 2r by 5. I wrote reverse, I guess. Yeah, I wrote reverse. Nay, like I messed up the friction part, I guess. 2r minus 5h. That looks right only. You can take Nashihari, there's nothing wrong with this. Previous one was only right. Did I do something wrong? I'm getting a weird feeling I reversed this 2r by 5. Ah, right only, because this result I derived with the assumption f is backward, isn't it? If I got f positive, means the direction I took was right. If I got f negative, that means the direction I took was wrong. That is the meaning of this. It doesn't mean actually, the friction is backward. F positive indicates our assumption of direction is right. So that will happen when h is greater than 2r by 5. Yeah, that looks good. Clear with this? We'll do a few more on this. You'll get the hang of it. But you can take any point about torque. But do you know the acceleration of any other point, Srihari? That's the reason we don't take. Clear with this? Now, if I just ask you one question like that, tell me the answer for this. What if I take a solid cylinder? No slipping. Let's say apply force F here. Find acceleration of center of mass. Get this fast. Second question, where should F be applied so the friction is 0? Same thing, I just change the shape. Get this, now you know how to do this thing. Same thing. So force F, mg, and friction. If you're on the ground, okay, and the ground is at rest, you can take about A. Be careful with that. If you're not on the ground, don't take A. Then torque about A will be you take this perpendicular distance, which is 2r, which is F into 2r. Then you should take moment of inertia about A. Moment of inertia about A, parallax's theorem, I about center of mass plus mr square. That will be 2fr is equal to, that will be mr square by 2 plus mr square alpha. So alpha will be 4f by, that will be 3mr. A is equal to r alpha, 4f by 3m. Got it? The second part of the question, where should F be applied so that the friction is zero? This is also cool. So now when you apply the force F, let's say you're applying at a height h. Normal reaction, friction is zero. It is given in the question, so there is no need to draw it, mg. And remember, A is still not slipping. So A can be still taken. So now torque about A will be F into h plus r is equal to 3mr square by 2 alpha. Right? And then we get F is equal to, we also know F is equal to ma. Take that and substitute there. That would be ma h plus r. That will be 3mr. R alpha is A again. So ma goes off. We end up with h is equal to r by 2. Clear with the steps. If friction is not there, you can put F0 in the FPT. Go, take a break. Come back by 9:47. We'll continue from here. Any doubt so far? And again, if you see, I didn't teach you, except that no slipping thing. I'm still using that same, the process. FBD, constraints, equations, and solving. Yeah, most of you got it right. Chalo, go take a break. Come back in 5 minutes. Get away from the screen. Don't keep staring at the screen for so long. Let's start off. Mass M, radius R, mass M, radius R. Solid cylinders. Let's say this is a hollow cylinder. The plank is also mass M. It's a long plank, so assume they'll not lose contact. And you're applying force F. There's no slipping at any surface. Find the acceleration of the plank. And find all frictional forces. Let's see how you do this. First, let's see how you get the FBD. If you got the FBD right, that itself is a thing. Other scams on. So we have a long plank. So the plank won't fall down, okay? It will be always in contact with them. But you kept them one on a solid cylinder, one on a hollow cylinder, same mass, same radius. And you're pulling the plank with a force F. And there's no slipping at any surface. Find the acceleration of the plank and all the frictional forces. Other scams on. Let's see the FBD, whether you got the FBD right. Force F. This friction will be F1. This friction will be F2. Frictions will be different. If both had been solid spheres, now you can argue because of symmetry they'll have same frictions. Now because both are not identical, you can't do that. Right? So the same friction will act here, F2. The same friction will act here, F1. This will be N1. This will be N2. This will be N2. This will be N1. Now there'll be one more friction here, F3. There'll be one more friction here, F4. Your own weight, mg. You have N3, you have N4. Check. This would be a free body diagram. If both had been solid cylinders, your life would have been a little easy. But let's see what happens now. Now let the axis of the plank be AP. Let this guy go with A1. Let this guy go with A2. Let this go with alpha 1. Let this go with alpha 2. There's no guarantee both the cylinders also will go with the same acceleration. This becomes lengthy. So let's see what happens to the equation. So when I write the force equations, F minus F1 minus F2 is equal to mass into acceleration of the plank. 1. Now, like I said, the bottommost point, if you're on a ground and the ground is not moving, these points are really good. So this is point A. Let's take this as point B. Now, when you take torque about A, literally N3, F3, mg, N2, everything goes off. Torque about A will be only F2. The distance is 2r. Remember, it's a hollow cylinder. Hollow cylinder is as good as a ring. Hope you remember the result. Hollow cylinder is like a ring. So when you use the parallaxes theorem, this is F2 into 2r. That will be I of a ring is mr square plus mr square alpha 2. So we end up with F2 is equal to 2mr square. This will be mr alpha 2. If you take torque about B, again same story. F4, N4, Mg, N1 will go off. We'll have F1 into 2r. This will be IB about alpha 1. This is one thing. Be careful. If you take torque about A, you should take I also about A. It looks common sense, but people accidentally put I centromass there. Now this will be solid cylinder. So this is mr square by 2 plus mr square, parallaxes theorem. So this will be 3mr square by 2. So 3mr alpha 1 by 4. That's your F1. Great. Then what about the no slipping condition? I need more space. So let's do it in the next page. So I can actually take these two and dump it here. This will be F minus mr 3mr alpha 1 by 4. Mr alpha 2 is equal to MAP. Okay. Now if we just look at the no slipping condition, this is going with A1, alpha 1. So this point will have acceleration A1 plus R alpha 1, and this point will have A1 minus R alpha 1, which is 0. So that means this guy is actually going with 2R alpha 1. I can do the same argument here, A2, and this is alpha 2. So this guy is going with A2 plus R alpha 2. This is A2 minus R alpha 2 is equal to 0. So this is also 2R alpha 2. And this is touching this point here and this point here. So no slipping condition at the topmost point will have acceleration of the plank must be equal to 2R alpha 2 and also 2R alpha 1. Great. I think now you got everything you want. So F minus 3m. What is R alpha 1? AP by 2. What is R alpha 2? AP by 2 is equal to MAP. Bring all APs to one side. That would be MAP 3 by 8 plus half plus 1. 3 by 8, 3 by 2, 4, 4, 3, 12 plus 3, 15 by 8. Acceleration of point P, 8F by 15M. There. That's your acceleration of the plank. Samyak, check. Did I do a mistake? You messed up somewhere. 3 by 8 plus half plus 1. Any doubts on this? How did I do this? It looks big, but it is solvable. That's what I said. If you take torque about A and B, you can eliminate F3, N3, F4, all will go off. And if the cylinder is going with A1 and A2, the topmost points will go with 2A1 and 2A2. So actually, we saw both the cylinders are actually going with same acceleration. So that's what I'm saying. You should not assume they're going with same. You assume they're different and let the science take care of it.
Sir, can you please show the last slide?
Yeah.
Sir, why didn't you include the pseudo forces torque in the torque equations?
Which torque equation? About B.
Sir, about both.
What is the acceleration of B?
Oh, my bad.
अभी तो पूरा स्टोरी वही है रे, 2 बार रिपीट कर रहा था. If you're on the ground, you can take that point. It'll take time, Ranvita. You're seeing it for the first time, na? But clear the steps. That's what I'm saying. See, if you have got till the equations part, I think you did a good job. That's it. Don't worry about the solving part. Solving part will take time. Until unless you guys solve another 40, 50 problems, at least practice, you won't get the hang of this thing. Initially, I wanted to give both solid cylinders. Then I had a feeling like, let's change it and see what happens. So if you ask me, this is the first time I'm doing this for myself also. I just changed it randomly, like hollow sphere, and let's see what happens. It was fine. I thought I'll get different accelerations. I didn't expect both will have same accelerations. Like, ठीक. That I think that is because of there's no slipping. Both had to become same accelerations. Now it becomes little more work. Now you can draw each FBD and solve F1, F2, F3, F4. I will leave it to you. That is work. But I think now if you got this, you'll be able to take everything. Now it is just lengthy. Clear with us? While taking torque about A, why don't we take N1? Because why? Utsa, you are talking about A and N1, you're comparing these two? Or are you talking about N2 maybe? N2. No, N2 is passing through A, na? Isn't it? It's a diameter point. N2 is passing through A, so it is 0. Clear with this? Let's make this a little more deadly. Now, if I have to ask an advanced paragraph question, this is what I'll ask. So we have a string wrapped around the cylinder. The floor is smooth. The plank is rough. Here, there is no slipping. Mass M, radius R, solid cylinder. This red one here is a string wrapped around it. So we have a string which is wrapped around a solid cylinder. And that string goes here through a pulley and then attached to a plank. On that plank, this cylinder is sitting. And now you're applying force F here. Find the acceleration of the plank, acceleration of the cylinder, and alpha of the cylinder. That would be the first question. I would ask you any one maybe. Find kinetic energy of the system after time t. If the force is pulling, the system will gain kinetic energy. Yeah, not really that tough, but process is still the same. Two FBDs, constant equation, no slipping condition, torque equation. So let's get this.
So mass of the plank is also m, right?
Same. Yeah. Let's take it same. Take a minute, get your FBD right properly. What is the access to the cylinder? I'm more keen on that. If you got that, then I think you got the equations right. Let's see the FPD. R by 2, 4 set. No. Right, Aditi. That was right. Have some confidence in it. You tell the answer and then you say no. Let's see the free body diagram. Plank, cylinder, force F. There will be friction. That same friction will act here. There will be tension, and this will be tension because these two are connected by the string. I'll not write mg, that is not needed. So anyway, it is not going up and down, so mg won't matter anyway. But if you want, I can still draw n downward. This will be n upward, and this will be mg. Now be careful. Don't take torque about A. A is accelerating now. A is accelerating horizontally with the acceleration of the plank, and I don't know the value. So that is how we know. So when to take that bottommost point when you're in a ground. So you can just remember like that. Next thing, the accelerations, acceleration of the plank, acceleration of the cylinder, and I'll take it as alpha. You can assume any directions. The science will take care. Next thing, no slipping condition. Now this is important. Listen, there are two things here. One is a no slipping condition. One is a string constraint. This point here is going with acceleration of the plank. This point here is going with a minus r alpha. This point here is going with a plus r alpha. And you have connected these two with the thing here, and this point is also going with AP. So this point A here and this, so acceleration of A must be equal to acceleration of the plank. So A minus R alpha is equal to AP. This is your no slipping condition. Next thing, when you're connecting this point here and this point here, this is the string constraint. Acceleration along the string must be same. Now be careful here. I got the signs a little reverse there. Alpha should have been the other direction. But here, so if acceleration along the string is same, so this will be A plus R alpha must be equal to minus of AP. Are you clear with this? So let me write this thing this way. So this point here is going backward with minus AP. Agreed? That point is actually going forward, isn't it? But we want along the string to be same. So this is your second equation. This is your string constraint. So there are two constraints here. And if you notice something, when you add them, if you add equation 1 plus 2, you will end up with A is equal to R alpha will cancel, and AP also will cancel. You'll get A is equal to 0, and you get AP is equal to minus R alpha. The cylinder is not accelerating only, meaning the cylinder will stay at the same place and will just keep rotating at the same place, and the plank is going forward. Are you clear with this? Please have a look at the no slipping condition and the string constraint. Any doubts on that part? Yashvi, clear with this? Sudiksha? Shaurya? Pratyasha? Ovia? Devanshi? Clear? So let's write the force equations. So these are the two conditions we have, and now if you write the equations, F minus tension is equal to mass into acceleration of the plank. And for the cylinder, F minus T is equal to ma. Then we'll take torque about the center of mass. Like I said, you can't take about A, so center of mass is always the safest point. But be careful here. I took the alpha direction wrong. That will be F into R plus T into R. Then I took I about center of mass, but I took alpha in the opposite direction. Because F ka torque is this way, T ka torque is this way. If that looks confusing, I will do this thing. F into R, K cap, T into R, K cap. This will be I into alpha minus K cap. So this will be F plus T, and I about center of mass will be solid cylinder. That will be mr alpha by 2. There. So we have A is equal to 0. That's one equation. A plank is equal to minus R alpha. That's your second equation. We have 5 equations and 5 unknowns. So take equation 1, substitute in 4. Take this and put it in 4. You will get F is equal to T. Then your equations become better. F minus 2F is equal to MAP. Then F plus T will be 2F becomes MR alpha by 2. But R alpha is nothing but MAP by 2. Take this and substitute there. That will be F minus 2F. But F is minus MAP by 4. Okay, same thing. We could have just kept 2F there. So 3 MAP. To F by M. Sorry, F by 2M. This is, sorry, minus n is there. I goofed up that part. There is a minus already there. That's a plus. That would be minus 2F by 3M. Anyone got that? Maria got it. Please check where it went wrong. That's what makes this question an advanced one. The question is still not over, but please have a look at the equations. If you got the equation, it is just a matter of solving. If you see, there are two constraints here, the string constraint and the no slipping condition. And you can't take torque about A because A is accelerating now. Any doubts on this? Yeah. Let's see one more. This is a good mains level question. So we have a no slipping there, and let's say we have a body here, mass M, radius R. And let the moment of inertia be I. So I'm not telling you what body is this, so we can keep different values of I and we'll get different answers. Let the height be h. The first one. Find the acceleration and time taken to reach the ground. Second thing, if body is a solid cylinder, find the minimum friction for no slipping. Again, for solid cylinder, if mu is half of mu minimum, so you need mu minimum to stop slipping, but you go only half of the value, then it will slip. Find V and omega when it reaches the ground. Let's get this. So the question is the other way over here. Where is the torque about? If you answer that, you'll get the answer for what you're asking. Where are you taking torque about? If you take torque about a certain point, then I also must be about that point. Let's see. Again, if you see here, the floor is at the incline is actually at rest. So you can actually take the torque about the bottommost point. What are the forces? Mg sine theta, mg cos theta, normal reaction, friction. Alpha, acceleration of the center of mass. Now, this point A, it's not moving because the ground is at rest. So I will take torque about A directly. Torque about A, there's only one guy, torque mg sine theta into R. This is what I'm saying. If you take about A, you'll get the answer in one step. Then you have to take moment of inertia about A. What is moment of inertia about A? I center of mass. Okay, you're asking what is the moment of inertia about this thing you're asking. If they don't say anything, it is generally center of mass on Lovia. I think you're asking about this one, I suppose. Yeah. So mg sine theta into R, this I will be I center of mass plus mr square. Now alpha, this value I gave it as I. So done, you'll get it in one step. A is equal to R alpha. So we get acceleration is equal to g sine theta by I center of mass, that is I by mr square. You can divide the whole thing by mr So R will R square. Hmm. So this will be, you can actually remember this result. Mains or a CET level question, this is. A is equal to G sine theta by I by MR square plus 1. That's the result for any body. So now I can give you solid cylinder, hollow cylinder, whatever it is, you will finish it off. And if this height is h, now this is going with a constant acceleration. So this will be h by sine theta. We can use s is equal to ut plus half gt square. So h by sine theta is equal to half into acceleration into t square. You will get the time from here. Root over 2h by a sine theta. That's your time. That was easy. Kinematics. Any doubts on this? Now get the remaining two parts. If the body is a solid cylinder, find the mu minimum for no slipping. And if you give mu is mu minimum by 2, now it will slip. Then find V and omega when it reaches ground. Get these two. Sine theta by 2. Okay, let's see. So for the B part, again, I will not use the formula. I'll try to derive it again. So we have the solid cylinder. Mg sine theta. Mg cos theta. Normal reaction. Friction. Acceleration alpha. Take this point A. The torque about A will be mg sine theta r is equal to I about A alpha. Now it is given this is a solid cylinder. So for a solid cylinder, moment of inertia is mr square by 2 plus mr square, that is 3mr square by 2 alpha. Alpha will be 2g sine theta by 3r. Acceleration will be 2 by 3 g sine theta. Then in the horizontal, along the incline, the forces will be mg sine theta minus friction is equal to ma. So we get friction is equal to mg sine theta by 3. But we know friction must be less than equal to mu into n, which is mu mg cos theta. Therefore, mu ka value must be greater than equal to tan theta by 3. So the mu minimum is 1/3 of tan theta. This is your mu minimum. Check. Now third part of the question. Now if I give half of this, that means if I give 1 by 6 tan theta, now it will slip. Now find the velocity and the omega when it reaches the ground. Then have a look at the steps. It's the same thing, repetition. Matlab. What about the third one? If mu is less than mu minimum, that means the body slips. Implies body slips. And F is maximum. So now when you draw the FBD, this will be F max, this will be N, this will be mg cos theta. You can't take torque about A because A is slipping now, A is accelerating. We can't take torque about A. So just be careful with that. You should know if it is not slipping, if it is on a ground, it is fine. Even though it saves you time, there is also a chance, mains may generally won't have an issue, but advanced may will get trapped. So what to do then? Nothing. You'll actually get the answers if you still use the equations. Now A will not be equal to R alpha. That is anyway there. Write the force equations. Mg sine theta minus F max is equal to ma. We get acceleration is equal to g into sine theta minus mu cos theta. And what about torque? You can take torque about center of mass. That always works. The only guy who is giving torque is F max into R. Now this will be I center of mass alpha. This will be mu mg cos theta into R is equal to, it's a solid cylinder, mr square by 2 alpha. Alpha will be 2 mu g cos theta by R. Check. Live with this. Now, how do you find V and omega? Tell me one thing. The cylinder, when it is rolling on the floor, it is traveling the distance because of A or alpha? What makes you travel linear distance? A or alpha? A, right? Alpha will never make you translate. So when I use the equation S is equal to ut plus half at square, S will be h by sine theta. Your acceleration will change. So from here, you'll get your time. This is important. Later on, when I teach you the work energy questions here, you will need this. What about omega then? Once you got the time, then I can use V is equal to U plus 80. So V is equal to 80. Similarly, I can use omega final is equal to omega initial plus alpha t. Time is still the same. Omega initial is 0, so alpha t. Because it's starting from rest. Clear with this? Any doubts on this? So using this is the actual G mains question. Tell me what is the answer for this guy. We have an incline theta. There is no slipping. So here we have a solid sphere. Cams on everyone. Hollow sphere. Ring. And a solid cylinder. Or a disc maybe, same thing. Who will reach first? How to do this? Get this, you know the result already now. This is actual mains question. Who reaches ground first and who reaches ground with more speed, something like that. There are questions. Who reaches first? Just now we calculated the acceleration, isn't it? A is equal to g sine theta, so numerator is same for all, by I by mr square. Maybe I should have said all have same mass and same radius. It won't matter, but should be. So there, now you can clearly see here, whoever has more I, right, that will give you less acceleration. If you have less acceleration, you'll get more time. So you'll go slower, isn't it? So it is clear. So out of all, who has the maximum moment of inertia? The ring. So the time taken for the ring is the maximum. After ring, who is the next highest moment of inertia? Hollow sphere, 2 by 3. Then disk, mr square by 2. Then solid sphere. So solid sphere will reach the ground first. Ring will reach the last. Mr square, 2 by 3 mr square, mr square by 2, and 2 by 5 mr square. Clear with this? The ring will reach the last. Same question. There is a slipping. Now who reaches first? If there is a slipping, friction is not sufficient. Now who will reach first? Just now we saw. If you are slipping, what happens? Friction is maximum. Then your acceleration becomes g sine theta minus mu g cos theta, independent of the body. All have same acceleration. So all will reach at the same time. Is that clear, everyone? The last case. What if we have a solid sphere MR? We have a solid sphere 2m2r. Two different solid spheres. Who will reach first? No slipping. Everything is same, just that one is a big ball and one is a small one. Who reaches the ground first? Again, go back to the equation. A is equal to g sine theta by I by mr square plus 1. Now, for a solid sphere, what is the result? 2 by 5 mr square. So that mr square will always cancel. Acceleration depends only on the shape. It doesn't depend on the mass and the radius. So they will take same time. Clear with this? Generally, people think, oh, the right one has more mass, so it'll have more acceleration and all, but that I by mr square will always cancel out. Clear? So that they can play like this. No slipping, different object, slipping, different object, same object, no slipping. Clear with this? So that's a bit about rolling and stuff. So next class when we catch up, we will do a little more and then we'll start off with the energy part in this. So if you see, we handled something like NLM and friction part of this. So in the next class, we will see circular motion and work per energy in rotation. Okay, with that, we'll wrap up for that day. right? And do remember there's a test online this week, so make sure to give it before Friday. So any doubts, anything else, please stay back and ask. We will catch up on Thursday again, same time. So take care, stay safe.